Right now, every atom in your body is obeying a set of rules. Gravity holds you to the floor. Electromagnetism keeps your cells intact. The strong nuclear force prevents your atoms from flying apart. You trust these rules the way you trust the ground beneath your feet. They feel permanent. They feel necessary. They feel like the bedrock of existence itself. But what if they aren't? In 2003, the philosopher Nick Bostrom published an argument so clean, so logically airtight, that it has haunted physicists and philosophers ever since. He didn't prove we live in a simulation. He did something worse. He proved that the probability is disturbingly high. And buried inside that probability is a consequence that almost nobody talks about. Not the glitches, not the codes hidden in equations. The real consequence. The one that should keep you awake tonight. If this reality is running on something, then something can turn it off. Not in a billion years. Not after some cosmic countdown. Right now. Without warning. Without reason. And you would never see it coming, because you are inside the thing that ends. In 2003, a philosopher at the University of Oxford published a paper that did something no paper in the history of philosophy had ever done before. It did not argue for a position. It did not defend a belief. It constructed a logical trap. A trap so elegant, so mathematically watertight, that once you walk into it, you cannot walk out. You can argue about which door you are stuck behind, but you cannot escape the building. The philosopher's name was Nick Bostrom. The paper was titled, "Are You Living in a Computer Simulation?" And the argument it contained has been quietly terrifying serious thinkers for over 2 decades. Not because it says, we are in a simulation. It does something far more sophisticated than that. It presents you with 3 options and proves, using nothing but probability theory and a handful of reasonable assumptions, that one of them must be true. And 2 of those 3 options are catastrophic. Let us walk through the logic, slowly, carefully, because this is not a casual hypothesis tossed off in a late-night conversation. This is a formal probabilistic argument, peer-reviewed and published in the Philosophical Quarterly. It has been analyzed by physicists, computer scientists, and mathematicians at institutions ranging from MIT to the Future of Humanity Institute, and in over 20 years, no one has been able to find a clean way to dismantle it. The argument begins with a single assumption. It is an assumption so mild, so widely accepted in neuroscience and philosophy of mind, that rejecting it creates more problems than accepting it. The assumption is called substrate independence. It states that consciousness does not require a specific physical material. It does not need to run on biological neurons made of carbon and water. It only needs the right kind of computational structure, the right pattern of information processing. If you could replicate the exact pattern of electrical and chemical signals that your brain produces, in silicon, in optical circuits, in any medium capable of performing the same calculations, then the resulting system would be conscious. It would have subjective experience. It would feel like something to be that system. This is not a fringe belief. It is the working assumption of the majority of researchers in artificial intelligence, cognitive science, and computational neuroscience. When we talk about the possibility of artificial general intelligence, we are already assuming substrate independence. When we talk about uploading minds into computers, we are assuming it. When we say that a sufficiently advanced machine could think and feel, we are assuming it. Bostrom simply took this assumption and followed it to its logical conclusion, and the conclusion is staggering. If consciousness is substrate independent, then it is theoretically possible to simulate a conscious mind inside a computer, not to create an imitation of a mind. Not to build something that acts like a mind, but is hollow inside. An actual mind. A mind that experiences. A mind that thinks it is real, that thinks it has a body, that thinks it lives in a universe made of matter and energy. And if you can simulate one mind, you can simulate billions. You can simulate an entire civilization. You can simulate a planet. You can simulate a universe. All you need is enough computational power. Now, how much is enough? Bostrom estimated this. He calculated the computational requirements for simulating the entire mental history of the human species, every brain, every thought, every sensory experience of every human who has ever lived. The number he arrived at was somewhere in the range of 10 to the power of 36 operations. That is a 1 followed by 36 zeros. It sounds like an impossibly large number. But here is the thing. It is not. It is well within the theoretical limits of what a civilization only slightly more advanced than ours could achieve. A computer the size of a planet, using technologies that are plausible extensions of our own, technologies like reversible computing or quantum processing or molecular nanotechnology, could perform this many operations. Not in a billion years. In a matter of seconds. This is not science fiction. This is an extrapolation based on known physics and the observed trend of exponential growth in computational power. If our civilization survives for another few centuries and continues to advance, we will almost certainly reach this threshold. We will have the power to simulate entire universes, populated by conscious beings who believe their experience is real. This is the setup. Now comes the trap. Bostrom constructed a trilemma. 3 propositions. He proved that at least one of them must be true. Not might be true. Must be true. The logic is airtight. Proposition 1. Almost all civilizations at our level of development go extinct before they reach technological maturity. They destroy themselves through war, through environmental collapse, through some unforeseen catastrophe. They never build the computers. They never run the simulations. The party is over before it starts. If this proposition is true, then the reason we are not simulated is because no one survives long enough to simulate us. The universe is a graveyard. Every species that reaches the point of almost being able to play God gets wiped out before it can. This is terrifying in its own right. It is a version of the Great Filter. It implies that technological civilizations are fundamentally unstable, that the very intelligence that allows a species to build nuclear reactors and artificial intelligence also dooms it to self-destruction. If Proposition 1 is true, humanity is almost certainly going to die, and soon by cosmic standards. Proposition 2. Almost all civilizations that do reach technological maturity choose not to run ancestor simulations. They have the power, but they refuse to use it. Maybe they develop ethical constraints that prohibit the creation of simulated conscious beings. Maybe they lose interest. Maybe they evolve into a form of intelligence that finds such projects pointless. Maybe they pass universal laws against it. Whatever the reason, they have the key to the simulation engine, and they deliberately throw it away. For this proposition to hold, it must be a near-universal trend. It cannot be the case that 1% of advanced civilizations run simulations. Even 1% would be enough to flood the cosmos with simulated realities. For Proposition 2 to work, essentially 0 advanced civilizations can choose to run these programs. Every single one must refuse. Across all of space and all of time, not a single species, not a single rogue individual, not a single bored posthuman intelligence decides to boot up an ancestor simulation. The restraint must be absolute and universal. Think about that. Think about the diversity of human behavior alone. Think about the fact that within a single species on a single planet, we cannot agree on anything. We cannot agree on climate policy, on economic systems, on basic human rights, and Proposition 2 requires every intelligent civilization in the history of the cosmos to unanimously agree not to run simulations. It requires a level of coordinated self-restraint that has no precedent in any system we have ever observed. biological or otherwise. It is not impossible, but it is profoundly unlikely. Which brings us to Proposition 3. If civilizations do survive to technological maturity, and if even a small fraction of them choose to run ancestor simulations, then the number of simulated realities will vastly outnumber the one original base reality. Think about it from a simple counting perspective. One base civilization runs 1,000 simulations. Each of those simulated civilizations, if they are detailed enough, might themselves run simulations within their simulations. The number of simulated worlds grows exponentially. For every one real universe, there could be billions or trillions of fake ones. And every single being inside those fake universes believes they are real. They feel real. They think real thoughts. They have real memories. They cannot tell the difference because there is no difference from the inside. Now, you are one of these beings. You exist. You are conscious. You have experiences. You believe you are living in the base reality, the original universe. But statistically, what are the odds? If there is one real universe and 1,000,000,000,000 simulated ones, then the probability that you happen to be in the real one is 1 in 1,000,000,000,000. The math doesn't care about your feelings. The math says you are almost certainly simulated. This is the trap. You must accept at least one of these 3 propositions. There is no fourth option. The logic exhausts all possibilities. Either civilizations always die before reaching simulation capability, or they always choose not to simulate, or we are almost certainly in a simulation right now. Pick your poison. But option 3 is the one that carries a consequence so profound that it restructures your entire understanding of what it means to exist. And here is what most people miss. Here is the thing that the casual conversations about simulation theory skip over. Here is the consequence that should change the way you look at every physical law, every constant of nature, every atom in your body. If we are in a simulation, then our reality is not fundamental. It is not the bottom layer. It is not the bedrock. It is a process running on something else. It depends on hardware that we cannot see. It depends on energy that we cannot measure. It depends on decisions made by beings or systems or processes that exist outside the boundaries of everything we call the universe. And anything that depends on something external can be affected by something external. This means that the universe you live in could be modified, paused, or stopped entirely. Not through any process within physics, but through an external decision that our physics cannot predict, detect, or prevent. The simulation could simply cease to be computed, and unlike every other existential risk we can imagine, this one leaves no wreckage, no aftermath, no moment of ending. It is not destruction, it is discontinuation. We will explore the full weight of what that means. But first, we need to understand why this is not merely a logical possibility. We need to understand why the actual structure of the universe, the behavior of particles, the architecture of space and time looks suspiciously like what we would expect if reality were running on a computational substrate. Let us be precise about what this means. We are not talking about a philosophical toy. We are not talking about a thought experiment you entertain for fun and then set aside. We are talking about a logically coherent scenario in which the permanence of reality itself is not guaranteed. The thing you call the universe, the thing that contains every galaxy and every atom and every moment of your life, might be a temporary computational process. And temporary does not mean it will last 1 billion more years. Temporary means it lasts exactly as long as the external system decides it lasts. That could be another 10 billion years. It could be another 10 seconds. There is no way to calculate the odds because the relevant variables are outside the simulation. Now, some people hear this argument and they shrug. They say, well, even if we are in a simulation, nothing changes. I still feel real. My experiences still matter. The simulation is all I have, so I might as well act as if it is real. And there is wisdom in that response. Pragmatically, you cannot live any other way. But intellectually, the shrug is a defense mechanism. It is a way of avoiding the vertigo, because the simulation hypothesis does change something fundamental. It changes the nature of physical law. In the standard view of science, the laws of physics are eternal, universal, and necessary. They are the deep structure of reality. They are not arbitrary. They could not have been otherwise. They are the way the universe must be. We discover them. We do not invent them. They are woven into the fabric of existence. But under the simulation hypothesis, the laws of physics are code. They are chosen. They are written by a programmer or generated by a process or selected from a library of possible rule sets. They could have been different. They might be different in other simulations running on the same hardware. The gravitational constant is not a deep truth about reality. It is a parameter in a program. The speed of light is not the cosmic speed limit imposed by the geometry of space-time. It is a variable that was set to a specific value, perhaps for efficiency, perhaps for aesthetics, perhaps for no reason at all. This is not a small shift. This is a revolution in how we understand the relationship between science and truth. If the laws of physics are contingent rather than necessary, then physics does not tell us about the fundamental nature of reality. It tells us about the local rules of a particular simulation. It is valuable. It is useful. It allows us to make predictions and build technology. But it is not what we thought it was. It is not a window into the deepest layer of existence. It is a user manual for the interface we are trapped inside. And Bostrom himself has acknowledged this. In subsequent papers and interviews, he has explored the implications. He has noted that a sufficiently advanced simulation need not be perfect. It does not need to simulate every atom in the universe. It only needs to simulate what is being observed. If no conscious being is looking at a distant galaxy, that galaxy does not need to be rendered in full detail. It can exist as a low-resolution approximation, a statistical placeholder, until someone points a telescope at it. Then the simulation fills in the details on demand. This is not unlike how a video game works. The world behind your back does not exist at full resolution. It is generated when you turn around. The processing power is allocated dynamically, focused on whatever the observers are paying attention to. If this sounds uncomfortably similar to the observer-dependent nature of quantum mechanics, that is not a coincidence. We will explore that connection in depth, because the strange behavior of particles at the quantum scale, the way they seem to exist in multiple states until they are measured, the way they refuse to have definite properties until an observer asks, all of this begins to look less like a mystery and more like a feature of a system that only computes what it needs to compute. But we are getting ahead of ourselves. Before we look at the physics, before we examine the evidence that the universe behaves like an information processing system, we need to sit with the foundational consequence for a moment longer. Because this consequence is not just one implication among many. It is the implication. It is the reason the simulation hypothesis is not just an interesting idea, but a genuinely terrifying one. The consequence is this: you do not own your existence. You did not earn it. It was not given to you by a universe that is obligated to sustain it. Your existence is a process running on borrowed hardware, powered by borrowed energy, permitted by an authority you cannot see, cannot communicate with, and cannot influence. You are not the player. You are not even the character. You are the pattern of electrons inside the console. And when the console is unplugged, the pattern does not go somewhere else. It does not float away into a digital afterlife. It simply ceases. Not death, cessation. The distinction matters. Death is an event that happens to a being within a reality. It is the end of a biological process. It is sad, it is final in many ways, but it happens inside a framework that continues to exist after you are gone. The atoms that made up your body are still there. The space-time you occupied is still there. The laws of physics that governed your existence are still running. Your death is a local event in a persistent universe. But simulation termination is not local. It is total. It is the end of everything. Not just you, but every atom, every star, every law, every moment. It is not the death of a character in a story. It is the burning of the book. The story does not end. It unexists. And here is the part that should make your stomach drop. There is no reason to assume we would get a warning. There is no mechanism within the simulation that could detect an impending shutdown. Any monitoring system we built would itself be part of the simulation. It would be like a character in a dream trying to set an alarm clock to wake up. The alarm clock is part of the dream. It has no connection to the world where the dreamer is sleeping. If the dreamer wakes up, the alarm clock vanishes along with everything else. This is what separates the simulation hypothesis from every other existential risk. Every other risk operates within the rules. Asteroid impacts are governed by gravity. Pandemics are governed by biology. Nuclear war is governed by physics and politics. We can study these threats. We can calculate probabilities. We can build defenses. But simulation termination operates outside the rules. It is an exogenous risk. It comes from a domain we cannot reach. We cannot study it. We cannot prepare for it. We cannot even think about it coherently because our thoughts are made of the same substrate that would be terminated. And this brings us to a realization that we will return to at the end of this journey. The simulation hypothesis does not just change what we know about reality. It changes what it is possible to know. The answers we seek about the permanence of existence may not live inside the simulation. They may live outside it. And outside is a place we may never be able to go. So this is where we begin, not with a comforting framework, not with a distant philosophical curiosity. We begin with a formal argument that says the probability of our reality being the original, the base, the real one, is vanishingly small. We begin with the consequence that if the argument is correct, then everything we call the universe is contingent, dependent, and revocable. We begin with the recognition that the most fundamental question a conscious being can ask, will I continue to exist, may have an answer that is not written anywhere in the laws of physics, because the laws of physics are inside the box, and the answer is outside it. Now that we have established the stakes, now that we understand what is at risk, we need to ask the next question. The question that turns this from philosophy into physics. Is there any evidence? Is there anything about the actual structure of the universe, the behavior of particles, the architecture of space-time that looks like what we would expect if reality were running on a computational substrate? Because if the universe is a simulation, it should leave fingerprints. It should have seams. It should betray the limits of whatever engine is generating it. And when we look at modern physics with fresh eyes, with simulation-aware eyes, what we find is not comforting. What we find is a universe that behaves suspiciously, almost embarrassingly, like a system that is processing information, a universe with a resolution limit, a universe with a speed cap, a universe that only makes up its mind when you force it to answer a question. The fingerprints are everywhere, and they have been hiding in plain sight for a century. There is a question that has haunted physics for over a century. A question so basic, so embarrassingly fundamental, that most scientists avoid asking it in public. The question is this: what is the universe made of? You would think we know the answer. We have had particle accelerators for decades. We have the Standard Model. We have catalogued quarks and leptons and bosons. We can name the forces. We can measure the masses. We can predict the outcomes of collisions with extraordinary precision. But when you press a physicist on what these particles actually are, When you ask not how they behave, but what they are at the deepest level, the answer gets strange. Because the deeper you dig into the foundations of physics, the more the solid material world dissolves. And what you find underneath is not smaller particles. It is not a finer grain of matter. What you find is information, pure, abstract, disembodied information. And that discovery, more than any other, is what makes the simulation hypothesis so difficult to dismiss. Let us start with the man who saw it first. John Archibald Wheeler was one of the titans of 20th century physics. He worked alongside Albert Einstein at Princeton. He mentored Richard Feynman. He coined the term black hole. He was not a mystic. He was not a philosopher looking for metaphors. He was a hard-nosed theoretical physicist who spent his career working on nuclear physics, general relativity, and quantum gravity. And in the final decades of his life, after spending more time staring at the equations than almost anyone alive, he arrived at a conclusion that stunned his colleagues. He summarized it in 3 words: it from bit. The phrase sounds like a slogan, but it is a radical ontological claim. Wheeler was asserting that every physical quantity, every particle, every force, every field, every element of what we call physical reality derives its existence from information, not from matter, not from energy, from answers to yes or no questions, binary choices, bits. He wrote that every particle, every field of force, even the space-time continuum itself, derives its function, its meaning, its very existence entirely from apparatus elicited answers to yes or no questions, binary choices, bits. This was not a casual remark at a cocktail party. This was a carefully considered position published in academic proceedings and discussed at the highest levels of theoretical physics. Wheeler was saying that the universe is not made of stuff, it is made of information. The material world is secondary. The information is primary. To understand why this matters, think about what information actually is. In the mathematical sense, information is the resolution of uncertainty. When you flip a coin and it lands heads, one bit of information has been created. A question has been answered. Before the flip, there were 2 possibilities. After the flip, there is one. That transition from uncertainty to certainty is the fundamental act of information. Now, apply this to physics. When you measure the spin of an electron, you are asking a yes or no question. Spin up or spin down. The electron does not have a definite spin before you measure it. This is not a matter of ignorance. It is a matter of ontology. The spin literally does not exist as a definite property until the measurement is made. The measurement creates the fact. It creates the bit. Wheeler argued that this is not a quirk of quantum mechanics. It is the fundamental mechanism of reality. The universe is not a collection of objects sitting in space. It is a network of information creating events. Every interaction between particles is an exchange of information. Every measurement is a question posed to nature, and nature's answer is a bit. The physical world is built from these bits, the way a building is built from bricks. But, unlike bricks, the bits do not have physical substance. They are abstract. They are mathematical. They are patterns. And if the universe is made of patterns rather than stuff, then the distinction between a physical reality and a computed reality begins to evaporate. This idea might sound abstract. It might sound like philosophy dressed up in physics language. But it has teeth. It makes predictions. And those predictions have been confirmed in one of the strangest places imaginable: the interior of a black hole. In the 1970s, a young physicist named Jacob Bekenstein was studying black holes under the supervision of John Wheeler himself. Black holes were already known to be exotic objects. They were regions of space-time where gravity was so intense that nothing, not even light, could escape. The boundary of a black hole is called the event horizon. It is a surface of no return. Once you cross it, you are gone. But Bekenstein discovered something about the event horizon that nobody expected. He discovered that a black hole has entropy. Entropy, in thermodynamics, is a measure of disorder. It is also, in a deeper sense, a measure of hidden information. It tells you how many microscopic configurations could produce the same macroscopic state. A cup of hot coffee has high entropy because the molecules inside could be arranged in trillions of different ways and you would not notice the difference. Bekenstein showed that a black hole also has entropy. It has hidden information, but the amount of information it can contain is not proportional to its volume. It is proportional to its surface area. This is deeply counterintuitive. If you have a warehouse and you want to know how many books you can store inside, you measure the volume. The bigger the warehouse, the more books. That is how storage works in 3 dimensions. But a black hole does not work this way. The maximum amount of information you can cram into a region of space is determined not by how much space there is inside, but by how much surface wraps around it. This result was formalized into what is now known as the Bekenstein bound. It sets an absolute upper limit on the information content of any finite region of space. And that limit is always proportional to the area of the boundary, not the volume of the interior. When Stephen Hawking independently derived the entropy of a black hole using quantum field theory, he confirmed Bekenstein's result. The number matched. The entropy of a black hole is equal to 1/4 of the area of its event horizon, measured in Planck units. This was one of the most important results in the history of theoretical physics, and its implication is staggering. If the information content of a region of space is determined by its surface area, then the 3-dimensional world inside that region might not be fundamental. It might be a projection. It might be encoded on a 2-dimensional surface and then reconstructed, rendered, displayed as a 3-dimensional experience. This is the holographic principle. It was first proposed by Gerard Hooft in 1993 and developed further by Leonard Susskind. The name comes from the technology of holograms, 2-dimensional surfaces that encode 3-dimensional images. When you look at a hologram, you see depth. You see objects that appear to occupy volume, but all the information is stored on a flat surface. The holographic principle says the universe might work the same way. The 3-dimensional reality you experience, the depth and volume and spatial extension of the world around you, might be a reconstruction from data encoded on a distant 2-dimensional boundary. You are not living inside a 3-dimensional space. You might be living inside a projection, a rendering, an image generated from a lower dimensional data structure. This is not speculation. It has mathematical backing. In 1997, the theoretical physicist Juan Maldacena published a paper that became one of the most cited in the history of physics. He demonstrated a precise mathematical equivalence between a theory of gravity in a 5-dimensional space and a quantum field theory without gravity on its 4-dimensional boundary. This is called the ADS-CFT correspondence. It proved, at least within a specific mathematical framework, that a universe with gravity can be completely and exactly described by information living on a surface with fewer dimensions. The interior is not independent of the boundary. The interior is the boundary, viewed from a different perspective. The 3-dimensional world is the hologram. The 2-dimensional surface is the data. Think about what this means in the context of the simulation hypothesis. If you were designing a simulation, you would want to minimize computational cost. You would want to store data efficiently. You would want the smallest possible data structure that could encode the largest possible world. A holographic architecture does exactly this. It encodes a 3-dimensional universe on a 2-dimensional surface. It compresses reality. It reduces the storage requirements by an entire dimension. The holographic principle is not proof that we live in a simulation, but it is proof that the universe stores its information in exactly the way a well-designed simulation would. Now, let us go further. Let us look at the resolution of reality. When you zoom into a digital photograph, you eventually see pixels. The smooth image breaks down into discrete squares of color. The image has a minimum resolution. Below that resolution, there is no more detail. There is nothing to find. The question is whether the universe has a minimum resolution too. And the answer, as far as our best physics can tell, is yes, it does. The minimum resolution of the universe is set by the Planck scale. The Planck length is approximately 1.6 times 10 to the power of minus 35 meters. The Planck time is approximately 5.4 times 10 to the power of minus 44 seconds. These are not arbitrary numbers. They are derived from the three fundamental constants of nature: the speed of light, the gravitational constant, and the reduced Planck constant. When you combine these constants in the right way, you get natural units of length and time that represent the absolute smallest meaningful scales in physics. Below the Planck length, the concept of distance ceases to have meaning. Below the Planck time, the concept of duration ceases to have meaning. Space-time itself becomes undefined. It becomes a quantum foam, a chaotic froth of probabilities where geometry dissolves. This is exactly what you would expect if the universe were a computational system with finite resources. Every computer has a clock speed. It has a minimum time step, the interval between one calculation and the next. It has a minimum spatial resolution, the smallest unit of data it can represent. The Planck scale looks suspiciously like these limits. The Planck time looks like the tick rate of the universe's processor. The Planck length looks like the pixel size of the universe's display. The smoothness of space-time at our everyday scale is just high-resolution rendering. If you had a microscope powerful enough to zoom in to the Planck scale, you would see the pixels. You would see the grid. You would see the discrete, granular, digital structure of reality. This idea has a long and serious intellectual history. In 1969, the German engineer and computer scientist Konrad Zuse, who built one of the world's first programmable computers, proposed that the universe is literally a cellular automaton. A cellular automaton is a grid of cells, each of which can be in a finite number of states, and which updates its state according to simple rules based on the states of its neighbors. Zuse suggested that the entire physical world, from the motion of galaxies to the chemistry of DNA, could be generated by such a system. He published a book called Calculating Space, in which he laid out the hypothesis in detail. It was radical for its time. It was largely ignored, but the core idea refused to die. In the 1980s, the physicist Edward Fredkin took up the banner. Fredkin was a professor at MIT and a pioneer in the field of digital physics. He argued that the universe is not merely described by computation. It is computation. Every particle is a bit. Every interaction is a logical operation. Every physical law is an algorithm. Fredkin's version of digital physics went further than Zuse's. He proposed that information is the most fundamental substance in the universe. More fundamental than matter. More fundamental than energy. More fundamental than space-time. In Fredkin's ontology, a rock is not an object made of atoms. A rock is a pattern of information being processed by the computational substrate of reality. The atoms themselves are data structures. The forces between them are subroutines. And the evolution of the physical world from one moment to the next is simply the execution of the universe's source code. This view received a massive boost in 2003 when the physicist Seth Lloyd, also at MIT, calculated the computational capacity of the universe. He treated the entire observable universe as a computer and asked how many logical operations it has performed since the Big Bang. The answer was approximately 10 to the power of 120 operations. He also calculated the maximum amount of information the universe can store, which he found to be approximately 10 to the power of 90 bits. These are specific, finite numbers. They are not infinity. They are not even close to infinity. The universe has a limited processing power and a limited memory. It is, in a very precise and quantifiable sense, a finite computer. Lloyd went further. He showed that the known laws of physics are consistent with the universe being a quantum computer. Not a classical computer, not a simple grid of on-off switches, but a quantum computer, one that uses the full richness of quantum mechanics to process information. Quantum computers exploit superposition, the ability of a quantum bit to be in multiple states simultaneously, and entanglement, the ability of quantum bits to be correlated in ways that have no classical analog. These properties allow quantum computers to perform certain calculations exponentially faster than classical machines, and they are precisely the properties we observe in the physical world. When a particle exists in a superposition of states, it is, from the computational perspective, a quantum bit holding multiple values simultaneously. When two particles are entangled, they are, from the computational perspective, two quantum bits sharing a joint state that cannot be decomposed into independent parts. The weirdness of quantum mechanics is not a bug. It is a feature. It is the signature of a quantum computational substrate. The universe does not just passively contain information. It actively processes it. It computes. And the laws of physics are the algorithms that govern the computation. Consider the implications. If information is the fundamental substance of the universe, then the distinction between a physical universe and a simulated universe is not a distinction of kind. It is a distinction of degree. A simulated universe is a universe where information is processed by a computer that exists in another reality. A physical universe, under the digital physics view, is a universe where information is processed by a computer that is the universe itself. In both cases, the underlying reality is informational. In both cases, what you experience as matter and energy and space-time is a higher-level description of a lower-level computational process. The only difference is where the computer is. And from inside the computation, from inside the experience of being a conscious pattern of information, there is no way to tell. This convergence between physics and information theory has accelerated in recent years. The physicist Eric Verlinde has proposed that gravity itself is not a fundamental force, but an entropic force, a macroscopic effect arising from the statistical behavior of microscopic bits of information on a holographic screen. In his framework, gravity is not something that exists in the base code of reality. It is an emergent phenomenon, like temperature or pressure. Temperature is not a fundamental property of individual atoms. It is a statistical property that arises when you have many atoms interacting. Verlinde argues that gravity works the same way. It emerges from information. It is a consequence of the way data is distributed and processed on the holographic boundary. If Verlinde is correct, then one of the four fundamental forces of nature is not fundamental at all. It is a computational side effect. The physicist Nima Arkani Hamed and his colleagues have discovered mathematical structures called amplituhedrons, geometric objects that encode the outcomes of particle collisions without any reference to space-time. In the traditional approach to particle physics, you calculate the probability of a collision by summing up contributions from every possible path a particle can take through space and time. It is an enormously complex calculation, but the amplituhedron gives the same answer directly as a single geometric volume, with no reference to space, no reference to time, and no reference to locality. The result emerges from a purely abstract mathematical structure. Space and time are not needed. They are not even present. The amplituhedron suggests that space-time is not the arena in which physics happens. It is the output of physics. It is the rendered image, not the code that generates it. Now let us gather these threads together. Wheeler told us the universe is made of information. Bekenstein showed us the universe stores its information on surfaces, not in volumes. The holographic principle told us the three-dimensional world might be a projection from a lower-dimensional data structure. The Planck scale told us the universe has a finite resolution, a minimum pixel size. Zuzi and Fredkin told us the universe could be a cellular automaton, a system of discrete cells updating according to simple rules. Lloyd calculated the universe's computational capacity and found it to be finite and specific. Verlinde suggested gravity is not fundamental but emergent from information. Arkani Hamed showed that the outcomes of physical processes can be calculated without any reference to space-time at all. Each of these results, independently, is a landmark in physics. Each has been published in major journals. Each has survived scrutiny. And each, independently, points in the same direction. The physical universe is not what it appears to be. It appears to be a vast, three-dimensional space filled with material objects governed by forces. But beneath that appearance, at the deepest level that our theories can reach, the universe looks like an information processing system. It stores data in the most efficient possible way. It has hard limits on resolution and processing speed. It exhibits the hallmarks of computational architecture, and its most fundamental constituents are not particles or fields, but bits of information. None of this proves we are in a simulation. Let us be careful about that. The universe could be fundamentally informational and still be the base reality. It could be that information is simply what reality is at the bottom level. It could be that the universe is its own computer, running on its own hardware, with no external operator. But consider the weight of the evidence. Consider the direction in which every arrow is pointing. If you were a detective and you walked into a room that looked like an office, with a desk, a chair, a computer, and filing cabinets, you would conclude that someone works here. You might be wrong. Maybe the room was staged. Maybe it is a museum exhibit. But the evidence overwhelmingly suggests a function. It suggests an office. In the same way, when we look at the deep structure of the universe and find holographic data storage, finite resolution, computational limits, emergent space-time, and information as the fundamental substrate, the evidence overwhelmingly suggests a function. It suggests computation. It does not tell us who is computing or why. It does not tell us if the computation is deliberate or natural, but it tells us that the architecture is there, the scaffolding is visible, the fingerprints are on the wall. And this matters enormously for the simulation hypothesis, because Bostrom's argument is a probabilistic one. It says that if civilizations can build simulations, then most conscious experiences are simulated. The strength of that argument depends on whether simulation is physically possible. And the information theoretic view of the universe makes simulation not just possible but natural. If the universe is already information, then simulating it does not require translating matter into code. The matter is already code. The translation has already happened. A sufficiently advanced computer would not need to simulate physics from scratch. It would just need to run the same algorithms that reality already runs. It would need to instantiate the same information processing rules that the universe already obeys. The barrier between real and simulated becomes paper thin. It becomes a question not of kind, but of location. Is the computation happening here, in this universe, on this substrate? Or is it happening there, in another reality, on another substrate? And from inside the experience, you cannot tell. This is why the informational nature of the universe is not just an interesting fact about physics. It is a load-bearing wall in the architecture of the simulation argument. It transforms the hypothesis from a philosophical curiosity into a physical possibility. It means the universe is already speaking the language of computation. It means the universe already looks like what a simulation would look like. And it means that the terrifying consequence we identified at the start, the possibility that our reality is contingent and revocable, is not undermined by physics. It is supported by it. The code is visible. The architecture is real. The question is no longer whether the universe could be a computation. The question is whether this particular computation is the final one, or whether it is running inside something else. Something we cannot see, something we cannot measure, something that holds the power to continue or to end this entire grand and fragile process that we call existence. And if the universe is information, then the specific values of that information, the particular constants and parameters that define our reality, become suspicious. Because those values are not random. They are not arbitrary. They are tuned. They are calibrated with a precision so extreme that it borders on the absurd. And if the universe is a program, then those values are not discoveries. They are settings. That is where we go next, into the uncanny precision of the physical constants, and into the question of whether fine-tuning is a clue that someone, or something, set the dials. There are about 26 numbers that define the universe. Not theories, not equations, not models. Numbers. Raw, dimensionless constants that appear in the fundamental equations of physics and cannot be derived from anything deeper. They are simply what they are: the mass of the electron, the strength of the gravitational force, the charge of the proton, the cosmological constant, the ratio of the electromagnetic force to the strong nuclear force. These numbers are not calculated. They are measured. We find them by doing experiments and writing down the results. And for decades, physicists assumed they were arbitrary. They assumed these numbers could have been anything. They assumed the universe just happened to have these values the way a coin just happens to land heads. No reason, no purpose, just chance. But when physicists began to investigate what would happen if these numbers were different, they discovered something deeply unsettling. The numbers are not arbitrary at all. They are balanced on a razor's edge. If you change almost any of them by even a tiny amount, the universe falls apart. Not in some abstract, far future, cosmological sense. It falls apart immediately. It falls apart in a way that prevents anything interesting from ever existing. No stars, no planets, no chemistry, no life, no structure of any kind. Just a featureless soup of particles, or a void of empty radiation, or a universe that collapses before it has time to form a single atom. The margin for error is not small. It is essentially zero, and the fact that we exist, that anything exists at all, implies that these numbers were set with a precision so extreme that it demands an explanation. This is the fine-tuning problem, and under the simulation hypothesis, it takes on an entirely new and deeply disturbing meaning. Let us look at specific examples. Consider the cosmological constant. This is the number that describes the energy density of empty space. It governs how fast the universe expands. In 1998, astronomers discovered that the expansion of the universe is accelerating. Something is pushing galaxies apart. That something is dark energy, and the cosmological constant is its measure. The observed value of the cosmological constant is extraordinarily small. It is approximately 10 to the power of minus 122 in natural Planck units. That is a decimal point followed by 121 zeros and then a 1. It is almost, but not quite, zero. And it has to be almost zero. If it were larger by a factor of even 10 to the power of a few, the expansion of the universe would have been so rapid that matter could never have clumped together. Gravity would have lost the race. No galaxies would have formed. No stars would have ignited. No planets would have condensed. The universe would have been a thin, cold, expanding mist of particles, forever flying apart, forever alone. If the cosmological constant were negative by a similar amount, the universe would have collapsed back on itself almost immediately after the Big Bang. It would have lasted a fraction of a second. Not enough time for a single proton to form, let alone a human being. The fine-tuning of the cosmological constant is so extreme that the physicist Steven Weinberg once called it the worst prediction in the history of physics. When physicists try to calculate the expected value of the cosmological constant using quantum field theory, they get a number that is roughly 120 orders of magnitude too large. That is not a small error. That is like predicting that a person weighs 10 to the power of 120 kilograms. The discrepancy between the predicted value and the observed value is the largest in the history of science. And yet, the observed value is exactly what it needs to be for the universe to support complexity. It sits in a vanishingly narrow window between too much and too little. A window so narrow that if you represented all possible values of the cosmological constant as a number line stretching from one end of the observable universe to the other, the life-permitting range would be smaller than a single atom. Now consider the strong nuclear force. This is the force that holds atomic nuclei together. It glues protons and neutrons into the dense cores of atoms. It is the reason that matter exists in forms heavier than hydrogen. If the strong force were about 5% weaker, deuterium, the simplest composite nucleus, would be unstable. Without stable deuterium, the chain of nuclear reactions that builds helium inside stars would fail. Stars would still burn, but they would burn differently. They would not produce the heavier elements, carbon, oxygen, iron, that are necessary for planets, for chemistry, and for life. The periodic table would be almost empty. The universe would be a sea of hydrogen, glowing faintly but incapable of producing anything complex. If the strong force were about 2% stronger, the consequences would be even more dramatic. Protons would fuse directly into diprotons, a nucleus made of 2 protons. This reaction would be so fast and so efficient that stars would burn through their fuel at a catastrophic rate. The sun, instead of lasting 10 billion years, would exhaust itself in a cosmically insignificant fraction of that time. There would be no stable era for planets to form, no long epoch for oceans to fill, no time for the slow, patient chemistry that builds molecules and eventually organisms. The universe would be a fireworks display, bright, brief, empty. Consider the ratio of the electromagnetic force to the gravitational force. Electromagnetism is roughly 10 to the power of 36 times stronger than gravity. That sounds like a design flaw. Why would one force be a trillion times stronger than another? But this ratio is critical. If gravity were stronger relative to electromagnetism, stars would be much smaller and would burn much hotter and much faster. They would not provide the stable, long-lasting energy source that life requires. If gravity were weaker, stars would not compress enough to ignite nuclear fusion. They would be cold, dark lumps of gas. The precise ratio between these forces creates a Goldilocks zone where stars can burn steadily for billions of years, providing a stable platform for the development of complex chemistry on orbiting planets. Consider the mass of the neutron relative to the proton. The neutron is roughly 0.14% heavier than the proton, a difference so small you could almost ignore it. This tiny difference determines the behavior of nuclear physics. If the neutron were lighter than the proton by even a small amount, protons would decay into neutrons, and hydrogen atoms would not be stable. Without stable hydrogen, there would be no water, no organic chemistry, and no stars powered by hydrogen fusion. If the neutron were heavier by a slightly larger amount, all neutrons would decay before they could be captured into nuclei during the first minutes after the Big Bang. The universe would contain only hydrogen, no heavier elements, no carbon, no life. These examples can be multiplied. The mass of the up quark, the mass of the down quark, the strength of the weak nuclear force, the number of spatial dimensions, the ratio of matter to antimatter in the early universe. Each of these quantities sits within an incredibly narrow band of life-permitting values. Shift any one of them by a small amount, and the result is a universe that is sterile, chaotic, or non-existent. The physicist Martin Rees identified 6 such numbers in his book Just 6 Numbers and argued that the life-permitting region of parameter space is vanishingly small compared to the total range of possible values. The physicist Leonard Susskind has described the fine-tuning as the greatest puzzle in all of physics. So how do we explain it? There are 3 main approaches, and each one leads to a radically different view of reality. The first approach is the anthropic principle. This is the weakest explanation, and it is essentially a tautology. It says that we observe the constants to have life-permitting values because if they did not, we would not be here to observe them. This is true but unsatisfying. It is like a lottery winner saying the reason they won is that only winners get to celebrate. The statement is correct. It explains why we see what we see, but it does not explain why the winning ticket exists in the first place. It does not explain why the constants have the values they do. It merely notes that we could not have noticed otherwise. The anthropic principle is a selection effect, not a causal explanation. The second approach is the multiverse. This is the dominant explanation in modern theoretical physics, and it has serious mathematical support. The idea is that our universe is not the only one. There are vast numbers of other universes, perhaps an infinite number, each with different values of the fundamental constants. In some universes, the cosmological constant is too large and everything flies apart. In some, the strong force is too weak and no atoms form. In a rare few, the constants are just right for complexity and life. We happen to live in one of those rare universes, not because someone chose the values, but because the sheer number of attempts guarantees that some universes will hit the target by chance. This is an elegant solution. It explains the fine-tuning without invoking any designer, but it comes with a price. The price is the existence of an unimaginably vast number of other universes, most of which are sterile and unobservable. Many physicists are uncomfortable with this. The multiverse is not directly testable. We cannot observe other universes. We cannot measure their constants. We must accept their existence on theoretical grounds alone. It works, but it requires a staggering amount of ontological baggage. You must accept that the overwhelming majority of reality is inaccessible and meaningless, just so that your tiny corner can make sense. The third approach is the one that the simulation hypothesis offers, and it is disarmingly simple. The constants are fine-tuned because they were tuned. They are not accidents. They are not the result of a cosmic lottery. They are parameters. They are settings on a control panel. Someone, or something, or some process selected these values because they produce an interesting result. A result that includes stars, chemistry, complexity, and consciousness. Under this interpretation, the fine-tuning problem is not a problem at all. It is a feature. It is exactly what you would expect if the universe were a designed system. Not designed in the religious sense, necessarily. Not designed by a bearded deity on a throne, but designed in the engineering sense. Configured, optimized, set up to run a particular kind of computation, a computation that requires matter, energy, structure, and time, a computation that requires observers. Now, it is important to be honest here. The simulation explanation is not more scientifically rigorous than the multiverse explanation. Both are unfalsifiable in the strict sense. Both require assumptions that cannot be directly tested. But the simulation explanation has a quality that the multiverse does not. It is parsimonious with existence. The multiverse requires an infinite number of real, physical universes. The simulation requires only one base reality and a lot of computing power. And, as we discussed earlier, the computing power required to simulate a universe is finite and calculable. It is large, but it is not beyond the reach of a sufficiently advanced civilization. The simulation hypothesis explains fine-tuning without multiplying universes. It explains it by multiplying simulations. But the simulation hypothesis does more than explain why the constants are what they are. It reframes what the constants are. In the standard view of physics, the constants are discoveries. They are facts about the deep structure of reality. They are woven into the fabric of existence. They cannot be changed because they are not parameters. They are properties of being. But under the simulation hypothesis, the constants are not properties of being. They are properties of the program. They are values assigned in a configuration file. They could have been different. They might be different in other simulations running on the same hardware. They might even be changed during runtime. And this leads to a deeply unsettling line of reasoning about the nature of physical law itself. If the universe is a computation, then every law of physics is an algorithm. Newton's law of gravitation is not a description of how masses interact. It is a subroutine that calculates the behavior of objects labeled as massive. Maxwell's equations are not a description of electromagnetic fields. They are a set of rules for updating the values of field variables at each time step. The Schrödinger equation is not a description of quantum states. It is a propagation rule for probability amplitudes. The laws of physics are not eternal truths carved into the bedrock of reality. They are code, and code can be written, edited, debugged, and replaced. This reframing has consequences. If the laws of physics are algorithms running on external hardware, then those algorithms must obey the constraints of that hardware. Every computer has limits. It has a maximum processing speed. It has a finite memory. It has a clock rate that determines how many operations it can perform per unit of time. If the universe is a computation, then we should expect to find evidence of these limits encoded in the structure of physical law. And we do. Consider the speed of light. In our universe, the speed of light is the absolute maximum velocity. Nothing can travel faster. No information can be transmitted faster. No influence can propagate faster. This speed limit is not just an empirical fact. It is woven into the geometry of space-time through Einstein's special relativity. It defines the causal structure of the universe. It determines which events can influence which other events. But why does this limit exist? In a truly infinite, truly analog, truly fundamental reality, there is no obvious reason why there should be a maximum speed. A speed limit implies a bottleneck. It implies that something is constraining the system. In a computational framework, the speed of light has a natural explanation. It is the maximum rate at which the simulation can propagate information across its grid. It is the speed at which the processor can update adjacent cells. If you think of spacetime as a cellular automaton, a grid of cells updating in discrete steps, then the speed of light is simply the rate at which a signal can travel from one cell to its neighbor in one time step. It is the diagonal of the grid. It is not a mysterious cosmic constant. It is a hardware limitation. Consider quantum indeterminacy. In quantum mechanics, particles do not have definite properties until they are measured. An electron does not have a definite position until you look for it. A photon does not have a definite polarization until you test it. Before measurement, these properties exist only as probability distributions. They are smeared out across all possible values. This is deeply strange from a classical perspective. Why would the universe leave things undecided? Why would reality be fuzzy? In a computational framework, This behavior has a natural and economical explanation. It is lazy evaluation. Lazy evaluation is a well-known technique in computer science. Instead of calculating every value in advance, a lazy system calculates values only when they are needed. It saves processing power by leaving things in an indeterminate state until a specific query forces a resolution. If the universe is a computation with finite resources, then maintaining every particle in a definite state at all times would be enormously expensive. It would require tracking the exact position, momentum, spin, and every other property of every particle in the universe at every moment. That is an astronomical amount of data. But if the system uses lazy evaluation, it can keep particles in a compressed, probabilistic state and only resolve them to definite values when something interacts with them. When a measurement is made, the system performs the calculation and returns a specific result. Before the measurement, the calculation has not been done. The property does not exist. It is not that the property is hidden. It is that the property has not been computed yet. This is a standard resource-saving strategy in any computational system. You do not perform calculations whose results no one is requesting. You store the variables in a compressed state and resolve them only when queried. Quantum mechanics looks like the physics version of this optimization. The universe does not calculate what it does not need to calculate, and it only needs to calculate what is being observed. Consider the Planck scale again, but now from the perspective of computational constraints. The Planck length and the Planck time define the smallest meaningful units of space and time. We have already seen why this looks like a resolution limit, but in the context of computational resources, it takes on additional significance. The Planck scale is not just a pixel size, it is a budget constraint. It tells us that the system has a finite granularity, a minimum step size below which no further computation is performed. And that granularity, combined with the speed of light as a maximum propagation rate and the Bekenstein bound as a maximum memory density, defines a complete set of hardware specifications for the machine that runs reality. The physicist Hans-Peter Bremermann calculated in the 1960s that there is a maximum rate at which any physical system can process information, given its mass and energy. This is known as the Bremermann limit. It states that no system can process more than approximately 1.36 times 10 to the power of 50 bits per second per kilogram. This is a hard physical limit derived from quantum mechanics and relativity. It means that even if you could build a computer out of the entire mass of the Earth, it would still have a finite processing speed. Seth Lloyd extended this analysis to the entire observable universe and found, as we discussed, that the universe has performed approximately 10 to the power of 120 operations since the Big Bang. It has stored approximately 10 to the power of 90 bits. These numbers are enormous by human standards, but they are finite, they are bounded, they represent a ceiling. Under the standard interpretation, these limits are simply properties of nature. They are what they are. But under the simulation hypothesis, they become something else. They become resource constraints. They tell us that the system running our universe has a finite computational budget. It can only do so much. It can only store so much. It can only process so fast. And every feature of physics that we observe, the speed of light, the Planck scale, the uncertainty principle, the quantization of energy, the holographic bound, every one of these can be reinterpreted as a strategy for staying within that budget. The speed of light caps information transfer rate. The Planck scale caps resolution. Quantum indeterminacy reduces the number of calculations needed. The holographic principle reduces data storage by a dimension. Quantization of energy ensures that the system deals with discrete, countable values rather than infinitely precise continuous ones. This is not proof. It is not a slam dunk argument that forces you to accept the simulation hypothesis. But it is a pattern. It is a pattern that should make you uncomfortable. Because every single feature of fundamental physics, every deep property of the universe that we have discovered over the last century, has a natural and economical interpretation as a computational optimization. The universe does not waste resources. It does not compute more than it needs to. It does not store more data than it needs to. It does not process faster than it needs to. It operates exactly the way a well-engineered simulation would operate. A simulation built by someone who understands efficiency. A simulation built by someone who has to work within limits. A simulation built by someone who, like every programmer who has ever lived, has to manage the trade-off between detail and performance. And this brings us to a thought that is both profound and disturbing. If the laws of physics are optimization algorithms, then they are not sacred. They are not eternal. They are not the deep truth of existence. They are engineering solutions. They are the best compromise that the simulator could find between fidelity and cost. They might be updated. They might be patched. They might be different in different regions of the simulation. They might change over time. We treat the laws of physics as the most reliable things in the universe. We build our entire civilization on the assumption that gravity will work the same way tomorrow as it does today. But if the laws are code, then that assumption is not guaranteed. It is a bet that the programmer will not change the settings, a bet that the system will not be rebooted, a bet that the parameters that govern our existence will remain what they are for reasons that we cannot access and cannot influence. We do not know why the constants have the values they do. We do not know why the speed of light is what it is. We do not know why the Planck length is the minimum resolution. We do not know because these questions point outside the system. They ask about the configuration of the program, not the behavior of the simulation. They ask about choices made before the universe began, or above the universe, or outside the universe, in a domain that our physics cannot reach and our instruments cannot probe. The fine-tuning is a fingerprint. The computational limits are a signature. And together, they paint a picture of a universe that does not look like a brute fact of existence. It looks like a project. A vast, intricate, precisely calibrated project, running on finite hardware, obeying finite rules, consuming finite resources, and producing, in one tiny corner of its computational grid, a species that has just barely enough intelligence to notice the seams. But noticing the seams is only the beginning. The real question is what those seams tell us about the fabric underneath. Because the universe does not just have limits that resemble computation. It has behaviors that resemble computation. Strange, counterintuitive behaviors that have baffled physicists for 100 years. Behaviors that only make sense if reality is not continuous, not predetermined, and not fully rendered at all times. Behaviors that look less like the properties of a material world and more like the artifacts of a system that is generating reality on the fly, moment by moment, observer by observer. And when you look at these behaviors with computational eyes, the mystery does not deepen. It dissolves. It becomes obvious. It becomes the expected output of a finite engine running the most efficient possible code. The glitches are not glitches at all. They are features, and they have been staring us in the face since the day we first split light through a crystal and watched a particle decide in real time what it wanted to be. For 100 years, quantum mechanics has been the most successful theory in the history of science. It predicts the behavior of atoms, light, and subatomic particles with a precision that borders on the supernatural. It has been tested in thousands of experiments. It has never been wrong, not once. The predictions of quantum theory match the observed results to more than 10 decimal places. It is the foundation of modern technology. Every laser, every semiconductor, every MRI machine, Every smartphone in your pocket depends on quantum mechanics being exactly correct. And yet, despite this staggering success, nobody understands it. That is not an exaggeration. That is not a rhetorical flourish. The physicist Richard Feynman, who won the Nobel Prize for his work in quantum electrodynamics, famously said that nobody understands quantum mechanics. He was not being humble. He was being precise. The math works perfectly. The predictions are flawless. But when you ask what the math means, when you ask what is actually happening beneath the equations, the answers are contradictory, paradoxical, and in some cases, disturbing enough to make grown physicists lose sleep. And the most disturbing thing of all is that the strange behaviors of quantum mechanics, the behaviors that make no sense in a material universe, make perfect sense in a computational one. Let us start with the deepest and most uncomfortable problem in all of physics, the measurement problem. This is not a technical glitch. This is not an edge case. This is the central mystery of quantum theory, and after a century of work, it remains completely unresolved. The measurement problem is this. According to the equations of quantum mechanics, a particle does not have a definite state until it is measured. Before measurement, the particle exists in a superposition, a ghostly combination of all possible states at once. An electron does not have a definite position. It has a probability cloud. A photon does not have a definite polarization. It has a blend of all polarizations simultaneously. This is not a limitation of our knowledge. It is not that the particle has a definite state and we simply do not know what it is. The math is unambiguous. The particle genuinely does not have a definite state. It is in all possible states at the same time. Then something extraordinary happens. You measure it. You ask the universe a question. Where is the electron? What is the photon's polarization? And the instant you ask, the superposition collapses. The probability cloud contracts to a single point. The electron is here, the photon is vertical. A definite fact has been created where none existed before. The universe has answered your question. But here is what keeps physicists awake. There is nothing in the equations that describes this collapse. The Schrödinger equation, the fundamental equation of quantum mechanics, describes the smooth, continuous evolution of the probability cloud. It never collapses. It never produces a single definite outcome. It just keeps spreading, getting more complex, incorporating the measuring device and the laboratory and the scientist and eventually the entire universe into one enormous superposition. The collapse is not in the physics. It is an add-on. It is a rule that we tack onto the theory by hand because we know from experience that measurements produce definite results. But the theory itself does not predict this. It does not explain why measurement is special. It does not explain what counts as a measurement. It does not explain why looking at a particle forces it to choose. In a purely material universe, this is a scandal. It implies that either the equations are wrong, which they are not because the predictions are perfect, or that something outside the equations, something not described by physics, is responsible for the collapse. This is the measurement problem, and in 100 years, no one has solved it. But in a computational universe, the measurement problem is not a problem at all. It is a design principle. Think about what the measurement problem is really saying. It is saying that the universe does not calculate definite outcomes until something requests them. It is saying that the system maintains variables in an unresolved state, a compressed, probabilistic state, until a specific interaction forces a resolution. This is textbook lazy evaluation. This is a standard optimization technique used in every modern computing system. A database does not perform a query until a user submits one. A web page does not load images until the browser scrolls to them. A game engine does not render geometry until the camera points at it. The universe does not collapse a wave function until a measurement is made. If the universe is a computation running on finite hardware, then this behavior is not mysterious. It is necessary. Maintaining every particle in the universe in a definite state at all times would require an astronomical amount of processing power. The number of particles in the observable universe is approximately 10 to the power of 80. Tracking the exact position, momentum, spin, charge, and every other property of each one at every Planck time step would be computationally ruinous. But if the system uses lazy evaluation, the cost drops dramatically. Most particles do not need to have definite states most of the time. They are not being observed. They are not interacting in ways that require definite values. They can sit in a compressed, superposed state, consuming minimal resources until something forces the computation. The collapse of the wave function is not a strange quirk of nature. It is the universe performing a just-in-time calculation. It is rendering reality on demand. Now, let us push deeper. Let us look at what happens when we try to investigate the boundary between the quantum world and the classical world. Because this boundary, if it exists, should tell us something about the architecture of the system. In the 1960s, the Irish physicist John Stuart Bell devised a theorem that changed the foundations of physics forever. Bell was interested in a simple question. Could the strange behavior of quantum mechanics be explained by hidden variables? Could particles secretly carry predetermined values that we simply cannot see? This was Einstein's hope. Einstein believed that quantum mechanics was incomplete. He believed that particles have definite properties at all times and that the randomness we observe is just a reflection of our ignorance, not a feature of reality. If Einstein was right, the universe was classical at its core. The weirdness was an illusion. Bell proved him wrong. He derived a mathematical inequality, now known as Bell's inequality, that sets a strict limit on the correlations between measurements of two entangled particles. If the particles carry hidden variables, if their properties are predetermined and no signal passes between them faster than light, then the correlations must obey this limit. The math is clean. The logic is airtight. And when physicists ran the experiments, starting with Alain Aspect in 1982 and continuing through increasingly rigorous tests over the following decades, they found that the correlations violated Bell's inequality, consistently, dramatically, without exception. The experimental violation of Bell's inequality was confirmed so decisively that in 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their work on this very problem. The result is now considered one of the most firmly established facts in all of experimental physics. What does the violation mean? It means that one of two foundational assumptions about reality must be false. The first assumption is realism, the idea that particles have definite properties whether or not anyone is looking. The second assumption is locality, the idea that nothing can influence anything else faster than the speed of light. Bell proved that you cannot have both. At least one must go. Most physicists have chosen to give up realism. They accept that particles do not have definite properties until measured. They accept that the universe is fundamentally indeterminate at the quantum level. But some physicists have chosen to give up locality instead. They accept that particles can influence each other instantaneously across any distance. Both options are devastating to the classical worldview. Both options destroy the picture of a universe made of solid, independent, well-defined objects sitting in a fixed space and evolving through a fixed time. And both options are perfectly consistent with a computational substrate. If you give up realism, you are saying that the system does not assign values to variables until they are queried. This is lazy evaluation. The simulation does not compute what it does not need to compute. If you give up locality, you are saying that two variables can be correlated regardless of their spatial separation. In a computer, this is trivial. Two variables in a program can be linked no matter where they are stored in memory. Physical distance is a property of the simulated world, not of the underlying code. In the code, everything is equally accessible. The entanglement between two particles separated by 1 billion light years is not a mystery if the particles are just two entries in the same data table. They are not far apart in any meaningful sense. They are neighbors in the memory of the machine. Now let us look at an experiment that takes the observer dependence of quantum mechanics to its logical extreme. The delayed choice quantum eraser, first performed in the late 1990s, is one of the most unsettling experiments ever conducted. The setup works as follows. A photon is fired at a double slit. Behind the slits, a special crystal splits the photon into two entangled twins. One twin, called the signal photon, travels directly to a detection screen. The other twin, called the idler photon, is sent on a longer path through a series of mirrors and beam splitters. The signal photon hits the screen and makes a mark. Its journey is over. It is history. Then, after the signal has already landed, the experimenters make a choice about the idler. They can either send it to a detector that preserves the information about which slit the signal photon went through, or they can send it to a detector that erases this information. Here is the result. When the experimenters later sort the data, they find that the signal photons whose idler twins had their path information erased formed an interference pattern on the screen. The signal photons whose idler twins kept their path information formed a clump pattern. The signal photon behaved differently depending on what happened to its twin in the future. The choice made after the signal had already landed determined how the signal had behaved before the choice was made. In a material universe, this is inexplicable. The past is the past. What is done is done. A photon cannot go back in time and change its behavior based on a future decision. But in a computational universe, this result has a straightforward interpretation. The system does not finalize the record until all relevant computations are complete. The signal photon's behavior is not written to the permanent log until the idler photon's fate is resolved. The system keeps the result in a buffer, a provisional state, and only commits it once the full calculation is done. This is not time travel. It is deferred rendering. It is the same principle that allows a spreadsheet to update a cell when you change a formula in a different cell. The cells are linked. The computation is holistic. The output is only finalized when all inputs are in. The fact that, from our perspective inside the simulation, the signal event appears to precede the idler event is an artifact of our experience of time. In the underlying computation, both events are part of the same calculation, and the calculation is not complete until both pieces are resolved. Now let us look at the physical structure of the universe for more direct evidence of computational architecture. If reality has a minimum resolution, a pixel size, then it might be possible to detect it experimentally. The physicist Craig Hogan at Fermilab proposed exactly this. He suggested that if space-time is quantized at the Planck scale, there should be a tiny, measurable noise in the positions of objects. Not thermal noise, not mechanical vibration. A fundamental jitter arising from the granularity of space itself. He called it holographic noise because it would be a consequence of the holographic principle. The idea that the information content of a three-dimensional region is encoded on its two-dimensional boundary. Hogan built an instrument called the holometer, one of the most sensitive position-measuring devices ever constructed. It consists of two laser interferometers, each 40 meters long, arranged side by side. The interferometers bounce laser beams back and forth and measure the positions of mirrors with extraordinary precision. If space-time is smooth and continuous, the two interferometers should produce independent noise. Their random fluctuations should be uncorrelated. But if space-time is granular, if it has a pixel structure at the Planck scale, then both interferometers should detect the same jitter because they are both sitting on the same grid. Their noise should be correlated. The experiment ran for several years, The initial results did not find the specific type of holographic noise Hogan predicted at the sensitivity level tested, but the experiment was groundbreaking in its approach. It demonstrated that the question of whether spacetime is discrete is not purely theoretical, it is experimental. It can be tested, and future instruments with greater sensitivity could push the search further. The absence of a detection at one sensitivity level does not mean the discreteness is not there. It means the pixels might be smaller than the instrument can currently resolve. The search continues, but even without detecting Planck-scale pixels directly, there is abundant indirect evidence that the universe has a granular, quantized structure. Energy is quantized. You cannot have an arbitrary amount of energy. It comes in discrete packets, quanta. Angular momentum is quantized. An electron orbiting an atom can only have specific, discrete values of angular momentum. Nothing in between. Electric charge is quantized. Every charge in the universe is an exact integer multiple of the electron charge. There is no half charge. There is no irrational charge. The universe deals in whole numbers. This is precisely the behavior you would expect from a digital system. A digital system does not deal in continuous values. It deals in discrete steps. It deals in integers. It deals in bits. The fact that every fundamental quantity we have measured turns out to be quantized, discrete, rather than continuous, is not a coincidence. It is the most basic signature of a digital substrate. The universe is not analog. It is digital. And it has been telling us this for over a century. We just did not want to hear it. There is another feature of the universe that becomes deeply suggestive when viewed through a computational lens. The cosmic microwave background radiation, the afterglow of the Big Bang, has a finite resolution. It is not infinitely detailed. The temperature fluctuations in the CMB, which are the seeds of all the large-scale structure in the universe, have a characteristic scale. Below a certain angular size, the fluctuations are washed out. They are smoothed. There is a natural cutoff. In standard cosmology, this is explained by the physics of the early universe. The fluctuations were damped by interactions between matter and radiation in the hot plasma of the first few 100,000 years. This is called silk damping, and it has a well-understood physical mechanism. But the effect is the same. The earliest image of the universe has a maximum resolution. It is like a photograph taken with a camera that has a limited number of megapixels. You can zoom in to a certain level and then the detail stops. There is nothing more to see. The image is finite. In a computational framework, this is expected. The initial conditions of the simulation do not need to be infinitely detailed. They need to be detailed enough to seed the structures that will develop later, but no more. The CMB is the initial condition of our universe, and it has a finite information content. It is a finite data set. And from that finite data set, the simulation has generated everything we see today. Galaxies, stars, planets, oceans, brains, all of it flows from a finite amount of initial data processed by finite algorithms on finite hardware. The Big Bang was not the creation of a universe from nothing. It was the loading of initial conditions. It was the boot sequence. Let us also consider the observer dependence of quantum mechanics from the perspective of resource allocation. In a simulation, computing resources are finite and precious. You do not waste them rendering things that no one is looking at. You allocate them dynamically, directing processing power toward the parts of the simulation that are currently being observed or interacted with. In quantum mechanics, particles behave as probability waves, exploring all possible states simultaneously until they are observed. At that point, they snap into a single definite state. The system resolves the computation and delivers a result. When the observation ends, when the particle is no longer being monitored, it returns to its probabilistic state. It goes back to being a cloud of possibilities. This is exactly what efficient resource allocation looks like. The system keeps unobserved regions in a low-cost, compressed state. It only expends computational effort on the specific interactions that are being queried. This explains one of the oldest puzzles in quantum mechanics, the question of whether the moon is there when nobody is looking at it. Einstein asked this question sarcastically, confident that the answer was obviously yes. But quantum mechanics genuinely suggests that the answer might be more nuanced. The moon, when no conscious observer is examining it at the quantum level, does not need to have every one of its atoms in a definite state. It can exist as a macroscopic approximation, a coarse-grained description that is good enough for gravitational calculations, but does not resolve the individual quantum states of its 10 to the power of 50 atoms. The system does not need to render the interior of the moon at full resolution. It only needs to maintain the moon's gravitational influence, its position, its approximate mass. The fine details can be left in superposition until someone sends a probe to look. This might sound like a stretch. It might sound like we are forcing a computational interpretation onto physics that is perfectly well explained by the standard quantum formalism. And that is a fair criticism. The standard formalism does describe these behaviors without invoking any simulation, but the standard formalism does not explain them. It describes the what without answering the why. It tells us that particles exist in superposition, but it does not tell us why. It tells us that measurement causes collapse, but it does not tell us what measurement is or why it has this special status. It tells us that entangled particles are correlated, but it does not tell us how the correlation is maintained across vast distances. The computational framework does answer these questions. Superposition is lazy evaluation. Collapse is just-in-time rendering. Entanglement is shared memory. The speed of light is the maximum propagation rate. The Planck scale is the resolution floor. Quantization is digitization. The observer dependence of reality is dynamic resource allocation. Each of these explanations is simple, intuitive, and consistent with the mathematical structure of quantum mechanics. They do not contradict the formalism, they explain the formalism, they give it a physical, or rather a computational, interpretation. And there is one more piece of evidence that deserves attention, one more feature of the universe that looks disturbingly computational. It is the unreasonable effectiveness of mathematics. The physicist Eugene Wigner wrote a famous essay with this title in 1960. He was struck by the fact that mathematics, which is a product of human thought, an abstract game of symbols and logic, turns out to describe the physical universe with breathtaking accuracy. Why should the universe obey mathematical laws? Why should the trajectories of planets follow the same equations that mathematicians derive on chalkboards? Why should the behavior of electrons be described by complex numbers and Hilbert spaces? Wigner called this unreasonable. He could not explain it. He simply noted it as a deep and puzzling fact. But in a computational universe, the effectiveness of mathematics is not unreasonable at all. It is inevitable. If the universe is a computation, then it is a mathematical structure by definition. A computation is a mathematical process. It operates on numbers. It follows rules that are expressible as equations. The laws of physics are mathematical because the universe is mathematical. It is not that mathematics happens to describe reality. Reality is mathematics. The unreasonable effectiveness is explained by the identity of the two domains. We are mathematical objects living inside a mathematical process, and our mathematics describes our world because it is our world. Let us gather these threads one final time before we confront the consequence. The measurement problem suggests the universe computes on demand. The violation of Bell inequalities shows that reality is either indeterminate or non-local, both consistent with a computational substrate. The delayed choice quantum eraser suggests the system defers finalization until all inputs are resolved. The quantization of energy, charge, and angular momentum shows the universe operates in discrete steps. The Planck scale reveals a minimum resolution. The holographic principle shows the universe stores data on boundaries, not in volumes. The cosmic microwave background has finite information content. The observer dependence of quantum mechanics mirrors dynamic resource allocation, and the unreasonable effectiveness of mathematics is explained by the universe being a mathematical computation. None of these facts, taken individually, proves the simulation hypothesis. Each can be explained within the standard framework of physics, but taken together, they form a pattern that is coherent, self-reinforcing, and deeply suggestive. The pattern says that the universe is not a thing, it is a process. It is not material, it is informational. It is not continuous, it is discrete. It is not independent of observation, it is responsive to it. Every deep property of physics points in the same direction. And that direction leads to a conclusion that we have been circling for some time now. A conclusion that we can no longer avoid. If the universe is a computation, then it is not self-sufficient. It depends on something that computes it. It depends on hardware, on energy, on a process that exists outside the boundaries of everything we call real. And anything that depends on something external is vulnerable to something external. It can be altered, it can be constrained, it can be stopped. The cracks in the code are not evidence that the simulation is breaking down. They are evidence that the simulation exists. They are the seams. They are the fingerprints. They are the places where the architecture shows through the wallpaper, and what they reveal is not a universe that is eternal and self-contained. They reveal a universe that is contingent, a universe that is running, a universe that could, at any moment, for any reason, stop. And it is that consequence, that single terrifying implication, that we must now face directly. Because understanding the evidence is only half the story. Understanding what the evidence means for you, for your existence, for the permanence of everything you have ever known or loved, that is the part that changes everything. We have arrived at the place where the threads converge. For some time now, we have been building a case. We started with a logical argument that said the probability of our reality being the original, the base, the one true universe is disturbingly low. We moved into the structure of physics and found that the universe stores its information like a hologram, encodes its data on surfaces rather than in volumes, and obeys hard limits on processing speed and memory that are indistinguishable from the constraints of a finite computer. We examined the physical constants and found them balanced on a razor's edge of precision, fine-tuned with a specificity so extreme that it looks less like an accident and more like a configuration. And we explored the quantum world and found a reality that does not commit to definite states until forced, that maintains correlations across impossible distances, and that defers its calculations until an observer demands a result. Every layer of evidence pointed in the same direction, toward a universe that behaves like a computation, toward a reality that is generated rather than given. And now we must confront what all of this means, not for physics, not for philosophy, for you, for the nature of your existence, for the permanence of everything you have ever assumed was solid, was real, was guaranteed to last. The terrifying consequence of the simulation hypothesis is not that you might be made of code instead of atoms. At the level of your experience, there is no difference. You feel what you feel. You think what you think. Your pain is real. Your joy is real. Your memories are real in the sense that they are genuinely encoded in whatever substrate produces your consciousness. The terrifying consequence is not about the nature of your experience. It is about the fragility of its foundation. Because if your reality is a computation, then your reality depends on something external, something you cannot see, cannot measure, cannot influence, and cannot predict. And that dependency changes everything. In the standard view of physics, the universe is self-contained. It is a closed system. It carries within itself everything it needs to exist. The laws of physics are not imposed from outside. They are properties of the universe itself. Space-time is not generated by a machine somewhere. Space-time is the fundamental arena. Matter and energy are not calculated. They simply are. The universe needs no permission to exist. It needs no external power source. It needs no operator. It runs on its own, by its own rules, for its own reasons, or for no reason at all. And crucially, it cannot be stopped. There is no off switch. There is no plug to pull. The universe will end, eventually, through heat death or vacuum decay or some other internal process. But it will end on its own terms. It will end because of its own physics. The ending is written into the system. It is part of the story. But if the universe is a simulation, none of this is true. The universe is not self-contained. It is dependent. It runs on hardware that exists in another reality. It consumes energy from a power source we cannot access. It executes code written in a language we cannot read. And it continues to exist only for as long as the external system allows it to. The laws of physics are not intrinsic properties of reality. They are the rules of the program. They were written. They were chosen. They could have been different. They could be changed. The constants of nature are not eternal truths. They are parameters in a configuration file. The gravitational constant could be updated between one Planck time and the next. The speed of light could be doubled. The charge of the electron could be set to 0. And you would never know. Because every instrument you use to measure these constants, every neuron in your brain that processes the measurement, every mathematical framework you use to interpret the result, is itself part of the simulation. You are inside the system that is being modified. You have no independent reference point. You have no way to detect the change because the detection apparatus is subject to the same change. This is not a hypothetical concern. This is a structural feature of any simulated reality. A simulation, by definition, is a system whose behavior is determined by external computation. The internal physics of the simulation is not fundamental. It is derived. It is a consequence of the code running on the external hardware. And the external hardware can do things that the internal physics cannot predict, cannot prevent, and cannot even describe. From inside the simulation, the external reality is not just unknown, it is unknowable. It exists in a domain that is ontologically separate from everything you can observe. It is not far away. It is not hidden behind a wall. It is in a different category of existence entirely. The relationship between you and the external reality is not like the relationship between you and a distant galaxy. You could, in principle, travel to a distant galaxy. You could observe it. You could measure it. But you cannot, even in principle, travel to the external reality. You cannot observe it. You cannot measure it. You cannot formulate a hypothesis about it that is testable within the simulation. The boundary is absolute. And this absolute boundary is what makes the simulation hypothesis genuinely terrifying. Every other existential risk that humanity has ever contemplated operates within the known framework of physics. An asteroid impact is a gravitational event. We can predict it. We can track it. We can, in principle, deflect it. A nuclear war is a chain of physical and political events. We can model it. We can deter it. We can survive it. Vacuum decay, the possibility that space itself could collapse to a lower energy state, is a quantum event within our own physics. It would be catastrophic, but it would be an event within the rules. It would obey the equations. It would happen for a reason that is, in principle, comprehensible. But simulation termination is not an event within the rules. It is the cessation of the rules. It is not a disaster that happens inside the universe. It is the disappearance of the universe. It is not governed by any law of physics because the laws of physics are part of what disappears. It is not predictable because prediction requires a model, and no model inside the simulation can model what lies outside it. It is not preventable because prevention requires agency, and no agent inside the simulation can act on the external hardware. Let us think about what termination would actually look like from inside. The answer is that it would not look like anything. It would not be experienced. There would be no moment of darkness. There would be no flash of awareness. There would be no final thought. The computational process that generates your consciousness would simply stop. Between one Planck time and the next, the calculation would not be performed. And because your awareness is a product of the calculation, your awareness would not transition to a new state. It would not transition at all. There would be no you to notice the absence. This is categorically different from death. When you die biologically, the atoms in your body continue to exist. The space-time you occupied continues to exist. The universe persists after your death. Your death is a local event in a continuing reality. But simulation termination is not local. It is total. Everything goes. Every atom, every photon, every grain of space-time, every moment of history, every unfinished thought, every sleeping child, every orbiting planet, not destroyed, not collapsed, uncomputed. The distinction between destruction and uncomputedness is important. Destruction implies that something happened, an event occurred, energy was released, a process unfolded. Uncomputedness implies that nothing happened. The process simply did not continue. There was no event, there was no moment of termination. There was just the last moment that was computed, and then nothing. Not even nothing. Because nothing is a concept that requires a framework to exist within, and the framework is gone. And we have no reason to believe we would receive a warning. There is no mechanism within a simulation that could detect an impending shutdown. Any alarm system we built would itself be part of the simulation. It would require the simulation to continue running in order to function. It is like trying to build a fire alarm out of paper. The fire destroys the alarm before the alarm can sound. The only entity that could warn us is the external operator, and we have no communication channel with the external operator. We do not even know if there is an operator. The simulation might be running autonomously. It might be a background process on a machine dedicated to other tasks. It might be one of trillions of simulations running simultaneously, none of them monitored, none of them valued, all of them disposable. This possibility that we are not the point of the simulation is perhaps the most humbling aspect of the hypothesis. We naturally assume that if someone built this universe, they built it for us. We assume we are the purpose. We assume our consciousness, our complexity, our culture, our science are the valuable output. But there is no reason to assume this. We might be a side effect. We might be noise. The simulation might have been designed to study galaxy formation, or dark matter dynamics, or the behavior of quantum fields at extreme energies. Our emergence as conscious beings might be an unintended byproduct, a mold growing in the corner of a petri dish that was set up to study something else entirely. If the operators are even aware of us, they might regard us the way we regard bacteria in a biology experiment. Interesting, perhaps, but not the point, not worth preserving. And even if we are the point, even if the simulation was designed specifically to produce conscious observers, there is no guarantee that it will run indefinitely. Experiments end. Computational resources are reallocated. Priorities change. Power grids fail. Civilizations that build simulations are themselves subject to the forces of entropy, conflict, and decay. If the base reality is a physical universe, then it obeys its own laws, and those laws include thermodynamics. The hardware running our universe will eventually degrade. The energy powering it will eventually be exhausted. The operators maintaining it will eventually die or lose interest. Our universe has an expiration date, and that expiration date is not written in our physics. It is written in theirs. This reframes the nature of physical law in a way that is philosophically devastating. For 300 years, science has operated on the assumption that the laws of physics are necessary truths. They are not contingent. They are not arbitrary. They are the way reality must be. Einstein sought a unified theory not because he thought the laws were designed, but because he believed the universe could not have been otherwise. The elegance of the equations was, for him, evidence of their inevitability. But the simulation hypothesis strips this inevitability away. If the laws are code, they are not necessary. They are chosen. They are one option among many. The inverse square law of gravity is not the only possible relationship between mass and force. It is the one that was programmed. The speed of light is not the only possible maximum velocity. It is the one that was set. The fine structure constant is not the only possible coupling strength for electromagnetism. It is the one that was entered into the configuration. This does not mean the laws are random. They might be optimized. They might be the most elegant solution to a specific computational problem. They might be the result of a long process of refinement, analogous to the way software is developed through iterations of testing and debugging. But optimized is not the same as necessary. A well-designed bridge is optimized for its function. It is the best solution given the constraints, but it is not the only possible bridge. It could have been designed differently. It reflects choices. And choices imply a chooser, or at least a choosing process. The laws of physics, under this view, are not the bones of reality. They are the furniture of a rented room. They are present. They are useful. They are well made. But they do not belong to us. They belong to whoever set up the room. And they can be rearranged or removed at any time. Consider what this means for the concept of time. In our physics, time is either a fundamental dimension of space-time, as in relativity, or an emergent property of increasing entropy, as in statistical mechanics. In either case, time is part of the system. It flows within the universe. It is governed by the universe's own laws. But in a simulation, the internal time of the universe does not need to correspond to the external time of the base reality. The simulation could be paused for 1,000 years of external time and then resumed, and no internal observer would notice any gap. The simulation could be run at double speed or half speed or variable speed. The simulation could be rolled back to a previous state and run forward again with different parameters. From inside, you would experience a continuous, smooth flow of time. You would remember the past. You would anticipate the future. But the actual computational process generating your experience might be anything. It might be intermittent. It might be non-linear. It might have already been stopped and restarted 1,000,000 times. You would never know, because your knowledge of the past is itself a product of the current computational state. If the simulation were rolled back to last Tuesday and rerun, you would not remember the first version. You would only remember what the current state of the simulation encodes. Your memories are not records of what actually happened. They are data structures in the current state of the computation. And data structures can be written, overwritten, and erased. This dissolves the concept of personal history in a way that is profoundly unsettling. You believe you have lived a life. You believe you were born, grew up, had experiences, made decisions, and arrived at this moment through a continuous chain of causes and effects. But if the simulation hypothesis is correct, that chain is not guaranteed to have happened. The simulation might have been initialized 5 minutes ago with a complete set of memories and physical states corresponding to a 13.8 billion year history. This is the Boltzmann brain problem applied to computation. It is cheaper, computationally, to create a single brain with preloaded memories than to simulate an entire universe for billions of years. If the operators are economizing, your entire history might be a dataset, not an experience. You might be brand new, preloaded with the illusion of age. Now, this particular scenario, the 5-minute hypothesis, is not unique to the simulation argument. It was raised by Bertrand Russell in the early 20th century as a philosophical puzzle about the nature of memory and evidence. But the simulation hypothesis gives it teeth. It gives it a mechanism. It transforms it from an abstract thought experiment into a concrete engineering possibility. If the universe is a computation, then creating a preloaded state is not magic. It is initialization. It is what every program does when it starts. It loads initial conditions. It sets variables. It creates a starting point that includes all the data needed for the simulation to run forward consistently. The Big Bang, in this framework, is not an explosion. It is a boot sequence. It is the moment the program begins executing. And the cosmic microwave background, the fossil light from the earliest moments of the universe, is not a relic of a real explosion. It is the initial data loaded into memory at startup. We must also confront the possibility that the simulation is not a single, isolated run. It might be one of many. If the external civilization has the computational resources to run one simulation, it almost certainly has the resources to run many, thousands, millions, trillions, each with slightly different parameters, each exploring a different region of the space of possible physical laws, each producing different outcomes, different histories, different species, different forms of consciousness. Our universe, with its specific constants and its specific history, might be one entry in an enormous database of simulated realities. We might be experiment number 7,422,000,000, running on a server farm alongside trillions of sibling universes, most of which contain nothing interesting, a few of which contain civilizations, and none of which know about each other. The multiverse, in this framework, is not a metaphysical extravagance. It is a file directory. And this brings us to the deepest and most personal implication of all. The question of whether any of this matters. If the simulation could end at any moment, if the laws could change, if your history might be preloaded, if your universe is one of trillions, then what is the point? Why care about anything? Why build anything? Why love anyone? This is the existential crisis at the heart of the simulation hypothesis. And it is here that we must be careful, because the temptation is to spiral into nihilism, to say that if reality is not fundamental, then nothing has value. But that conclusion is wrong. It is wrong for a reason that is subtle, important, and ultimately liberating. The value of your experience does not depend on the substrate that produces it. Think about a piece of music, a symphony by Beethoven. You can play it on a grand piano. You can play it on a synthesizer. You can play it on a computer speaker. The substrate changes. The experience is the same. The beauty is the same. The emotional impact is the same. The music does not become less real because it is played on a digital instrument instead of an analog one. The music is the pattern, not the material, and you are a pattern too. Your consciousness, your feelings, your relationships, your creative acts, these are patterns. They are real at the level of the pattern regardless of what generates them. If you are a computation, you are still you. If your love is generated by an algorithm, it is still love. The warmth is real, even if the fireplace is virtual. But there is a difference between saying that your experience has value and saying that your experience is safe. Those are two different claims. And the simulation hypothesis grants the first while destroying the second. Your experience matters, your life matters, your choices matter at the level of the pattern. But the pattern is not permanent. The pattern depends on the continuation of a process you cannot control. And that combination of deep value and deep fragility is the emotional core of the simulation hypothesis. It is what makes it genuinely terrifying rather than merely interesting. It is the same terror that a parent feels watching a child sleep. The child is beautiful. The child is precious. The child is everything. And the child is vulnerable. The parent cannot protect the child from every possible danger. The parent cannot guarantee that the child will be safe forever. The love is infinite, but the control is finite. That is the human condition. And the simulation hypothesis says that the human condition is also the cosmic condition. Our universe is precious. It is complex. It is beautiful. It has produced consciousness and art and science and love. And it is vulnerable. It is contingent. It depends on something it cannot see and cannot touch. And it could be gone in an instant, not because it did something wrong, but because the process that sustains it is not obligated to continue. This changes the way we should think about science. For 3 centuries, the project of physics has been to discover the fundamental nature of reality, to find the deepest laws, to reach the bottom. But the simulation hypothesis suggests there may not be a bottom, at least not one we can reach. The laws we discover might be local rules. They might describe the behavior of the simulation but tell us nothing about the reality that runs it. Our physics might be complete within its own domain and yet utterly silent about the most important question of all. Will this continue? It also changes the way we should think about existence itself. We have always assumed that existence is binary. Something either exists or it does not. But in a computational framework, existence is a spectrum. A running program exists in a different way than a stored program. A stored program exists in a different way than a deleted program. A deleted program might still exist as fragments on a hard drive, recoverable in principle but not in practice. Our universe, as a computation, could exist in any of these states. It could be running, it could be paused, it could be stored, it could be archived, it could be partially corrupted, it could be backed up somewhere, waiting to be restored. The ontological status of our reality is not fixed. It is a function of what the external system is doing with it right now, and we have no way to check. Let us sit with this for a moment. Let us feel the full weight of it. You are sitting here, processing these ideas, feeling your body in whatever space you occupy. The room around you seems stable. The laws of physics seem reliable. The future seems open. But if the simulation hypothesis is correct, then the stability you feel is a local property of the computation, not a global guarantee. The reliability of the laws is a feature of the current code, not an eternal truth. And the openness of the future is bounded by a boundary you cannot see, a boundary that is not written in any equation you will ever discover, a boundary that exists in a reality you will never visit. The simulation hypothesis does not tell us that reality is fake. It tells us that reality is real but not fundamental. It tells us that existence is genuine but not guaranteed. It tells us that the laws of physics are true but not necessary. It tells us that the universe is vast and ancient and magnificent, and also, possibly, a finite process running on finite hardware, subject to finite decisions made by finite beings in a reality we cannot imagine. This is the terrifying consequence. Not that we are unreal, but that we are real and fragile, that the deepest truths we can discover about our universe might be surface features of a deeper system, that the ground we stand on is solid, but it is not the ground. It is a floor, built over a void, and the floor could be removed. And if this sounds like a reason to despair, consider the alternative. Consider what it would mean if the universe were truly fundamental, truly eternal, truly self-contained. It would mean that everything is necessary. It would mean that nothing could be otherwise. It would mean that the laws are locked, the future is fixed, and the story is already written. There would be safety in that. But there would also be a prison. The simulation hypothesis, for all its terror, preserves something that a deterministic, self-contained universe might not. It preserves the possibility that things could be different. It preserves the possibility of surprise. It preserves the strange, vertiginous freedom that comes from knowing that the rules are not carved in stone, that the ground is not the final ground, that there is something else, something beyond, something outside the borders of everything we know. We cannot reach it, we cannot see it, we cannot prove it exists, but the logic points to it, the physics whispers about it, the fine-tuning hints at it, the quantum strangeness gestures toward it. And the formal structure of Bostrom's argument calculates that the probability is high, not certain, but high enough to take seriously, high enough to change the way you look at the stars tonight, high enough to make you wonder, just for a moment, what is on the other side of the sky? We started this journey with a simple observation. You trust the laws of physics, you trust the ground, you trust that the universe will be here tomorrow, and we have spent this time showing you why that trust, while practical, is not guaranteed. The simulation hypothesis does not destroy your world, it reframes it. It takes the universe you know and places it inside a larger question. A question that physics cannot answer. A question that philosophy cannot settle. A question that sits at the very edge of what it is possible for a conscious being to ask. The question is not whether the universe is real. The universe is real enough to contain you, and that is real enough by any standard that matters. The question is whether the universe is all there is, whether the reality you inhabit is the final reality, whether the laws you discover are the final laws, whether the existence you experience is self-sustaining or borrowed. And the honest answer, the answer that the best science and the best philosophy can offer after 20 years of analysis, is that we do not know. We do not know if we are in a simulation. We do not know if the universe is fundamental. We do not know if the computation will continue. We know the argument is valid. We know the evidence is suggestive. We know the probability is not zero. And we know that if the hypothesis is correct, then we are living inside something that is not permanent, not autonomous, and not guaranteed. That is the terrifying consequence. Not a monster in the dark, not an alien invasion, not a cosmic explosion, something quieter, something deeper. The possibility that the fabric of reality itself is not the final fabric, that beneath the atoms and the fields and the forces and the space-time, there is a process, and the process is not ours, and the process could stop, and if it does, we will not be here to ask why. We will not be anywhere, because the anywhere was part of the process, and the process is the only thing that was ever real.